In this video, we'll be discussing foundational machine learning ideas that will be very generally useful, both in fighting overfitting and in the general model building and evaluation process. As a review from last time, overfitting occurs when a model follows the noise in data too closely. For example, if our model is to be used to identify cat pictures, the model we have described on the right overfits to our data because it's too specific to this particular cat. Overfitting is a hugely important and recurring theme in machine learning. How can we combat overfitting? Let's build up some essential ideas. The first idea is that it is very easy to overfit on the data that we already have if we have enough predictors. We can keep tweaking what predictors are added and how, and we'll do amazingly on our existing data. Given that, we shouldn't evaluate our model on the data we used to build it. We'll call this set of data the training set. Synonyms for model building that you'll see throughout the machine learning literature are training, fitting, building, and learning the model. If we have a specific set of data, the training set, for learning our model, we should have a separate data set for evaluating our model. This data set will be called the test set. Having a test set allows us to estimate our model's overall or true error rate on any new data. What is meant by true error rate? This is the mean squared error that would result if we could use our model to make predictions for everyone in the target population. This last point is important to emphasize. In machine learning settings where prediction is the main goal, we really only care about how our model predicts on new data. Therefore, we really need new data that we have not seen before or that was not used to build our model. We need both training and test data. Is this generally feasible? Let's talk about some practical issues. For one, what if we only have one data set? A solution, if the data set is big enough, is to randomly split that data set into a training and a test set. How big is big enough? This is pretty context dependent, but hundreds of observations is likely the minimum. We need enough data in the training set to build a reasonable model and enough data in the test set to estimate the true error rate well, which means that the data should be fairly representative of the target population in which we want to use our model. How much data should be in the training and test sets? In other words, what should the split be? Keeping in mind our answer for the big enough question, a good heuristic to start with is 80% for training and 20% for test. This approach of randomly splitting the one original dataset into two parts is called the validation set approach because the second subset of data not used for training is conventionally called the validation set or holdout set. Schematically, the validation set approach looks as follows. We start with the original dataset with n cases. Then we randomly split this data into a training set in blue, used to fit our model, and into a validation set in orange, used to estimate the test error. It's important for the split to be random in case the data have been sorted, so that you don't end up with all of group 1, say, in the training set and all of group 2 in the validation set. This approach is simple, but it does have some problems. One concern is that we are not fully using the data we have to build the model, and models built on less data tend to be poorer. Another concern is that of variability. What if the particular random split we use is a bad one? One example of a bad split could be if the training and validation sets end up looking like very different populations. Or it could be that this particular random split resulted in a large over or underestimate of the true error just by chance. Can we resolve these concerns somehow? It turns out that we can use a general technique called cross-validation to rectify these issues. Let's go through this technique. In cross-validation, we split our original training data into several parts, called folds, where each fold contains a subset of the cases. Breaking the data into k folds is called KFold Crossvalidation. The special case where k is equal to the sample size is called leave one out cross-validation. We hold out one fold for evaluating our model. This fold is called the validation or test fold, and reserve the other k-1 folds for training. We repeat this process k times for every possible validation fold. This gives us k mean squared errors, one for each possible validation fold, and we estimate the test error with the average of these k errors. Let's go through KFold cross-validation again in pictures. We randomly split our training data into 10 folds, indicated by the 10 blue boxes. In the first iteration of 10-fold cross-validation, we fit our model on the data in folds 2 through 10 and use fold 1 to compute mean squared error. For example, we may be investigating a linear regression model with predictors x1 and x4, and we fit this model on the data in folds 2 through 10. On fold 1, we compute the mean squared error for this model. We do similarly for the second fold, fitting the linear regression model on data from fold 1 and folds 3 to 10, and we compute the mean squared error on fold 2. We do similarly for all other folds. This gives us 10 mean squared errors. We average these 10 mean squared errors to get the 10-fold cross-validated mean squared error. This cross-validated error estimate is an estimate of the true error rate of our model on new data. Let's return to our concerns about the validation set approach. Does cross-validation actually address these concerns? Remember that our first concern was that poor models result from using only a small subset of the data. Cross-validation does address this concern because if we choose k appropriately, the k-1 folds used for training will have more data than in the validation set approach. What about the second concern, that we might get a bad random split just by chance? With cross-validation, we do this random splitting several times. Even if we do get one bad split just by chance, we estimate the true error with an average over the k-splits, which gives a more stable estimate of the true error. In summary, from the predictive viewpoint of machine learning, we care about estimating the true error rate of our models on completely new data. This leads us to the idea of having a dataset reserved for model fitting, called the training set, and a dataset reserved for estimating the true error rate, the test set. If we don't have separate datasets, an approach for getting them is to split our existing data. This is called the validation set approach. This approach is simple, but it has drawbacks in that it could leave too little data for training, or it could result in a bad split just by chance. A general technique that fixes these drawbacks is called cross-validation. This technique iteratively splits the data and estimates true error rates with an average over iterations. Throughout the course, we're going to rely heavily on cross-validation when we want estimates of the true new data error rate to inform choices that we make during model building.